everyone, and thank you for tuning in. My name is Priya, and I'm a policy fellow with QBTCI. And today I'm really glad to be joined by Pranay Kotasthane, who is the Deputy Director of the Takshashila Institute and chairs their high-tech geopolitics program. So if you've been following any conversation in India around tech, supply chains, and strategic autonomy, you've almost certainly come across his work. Pranay is the co-author of When Chips Are Down, Missing in Action, We the Citizens, and he also co-writes the newsletter Anticipating the Unintended and co-hosts Puliyabazi, which is a podcast on politics, policy, and tech. What makes today's conversation especially interesting is that before all of his policy work, Pranay actually spent years doing integrated circuit design at two Fortune 500 companies. So he's looked at the hardware up close, and now he spends his time thinking about the policy and geopolitics surrounding it. And that's exactly the lens we want today, because we are going to be talking about quantum supply chains. And so we're really glad. Thank you so much for joining us, Pranay. And with that, let's get straight into the questions. So quantum computing at the moment, when you look at the global ecosystems and you look at players like IBM, Google, IonQ, they're in their vertically integrated phase in that they make most of they do the full stack. But then there is some specialization. For instance, Blue Force for dilution refrigeration. If they want to do control electronics, then they usually get it from companies like Zurich Instruments in Switzerland or Q-Blocks in the Netherlands. So there is some specialization. And I want to know from your experience in the semiconductor ecosystem. I believe even the semiconductor industry started off vertically integrated, and then they started branching off and unbundling. So could you tell us a little bit about how this unbundling happened, how it emerged, a bit about the evolution of that?
Right. So that's a great question to apply to the quantum space and learn from semiconductors. See, the question we have to answer is, will this be a heavy capital cost industry? And if it is a heavy capital cost industry, the natural thing which happens is you can't reinvest capital with every new generation of technology for an infinite period of time. So that's essentially what happened in semiconductors. Is earlier, as you rightly said, there were vertically integrated firms. Most of the firms were actually memory firms. Not logic was not that complicated, and those memory firms were largely vertically integrated. They did by that we mean they did the design, they did the fabrication, they did the assembly, packaging, and they got the chips out. Right. So. Eventually, we know that a fabless foundry model appeared, where most of the top companies that we know of, NVIDIA, AMD, Qualcomm, they have no manufacturing capabilities. They only do the design part, and then they get it contract manufactured from players like TSMC for the manufacturing side, and then on the assembly side, there are players like JCET, Amcor, etc., which do the assembly. Right? So why is it that this kind of model emerged? So this unbundling was not a conscious strategic decision by a government or by a group of governments. It was a market response to a structural cost problem. Because what we people know of Moore's law, but there's also the Moore's second law, which is also called the Rock's law. So just as the process nodes become smaller and smaller, your transistors become smaller and smaller, the capital cost of a semiconductor fab doubles every 4 years. That is what is known as the Rock's law. So again, it's a heuristic. It's not a law, but the heuristic has stayed true. And in fact, the costs every time you go to a lower technology node, the costs keep ballooning significantly. Right? So imagine a company in the 1980s which is trying to go from a micrometer to half a micrometer. And if when it is doing that, it is going to have to do double the capital cost every 4 years. And those costs started becoming prohibitive after a point of time for companies and for governments. So there was this opportunity for players to think of it differently. And that's
Mm-hmm.
when somewhere some companies started doing ASICs before,
Mm-hmm. Yeah.
application specific integrated circuits. And then some other companies said, oh, we'll go even one step further and we can
Mm-hmm.
offer contract manufacturing. So there was
Mm-hmm.
think companies like TSMC, which came up in 1987, really pioneered this
Mm-hmm.
model. So they made two promises to their customers. One, they said that we will do contract manufacturing for you. That is, you give us the design. You don't have to bother about manufacturing at all. And this way they can attain scale, right? The only way you
Mm-hmm.
can justify doubling of capital cost every 4 years is if you keep your fabs completely occupied,
Mm-hmm.
right? And you mass produce products. Now, if you are one company, you're not going to be able to do that.
Right.
It depends on the demand for your product. But if you are a contract manufacturer, you can always fill your supply line with multiple customers, right? So that was
Mm-hmm.
one promise, that we can do contract manufacturing. And the second promise was that we will never compete with you, because one
Right.
risk that companies would have faced is, imagine you are the contract manufacturer and I give you the design. And what if you learn from my design and start
Right.
out competing me? So that
Mm-hmm.
was a promise of TSMC, that we'll not compete with you and we'll do contract manufacturing. So
Mm-hmm.
this was the beginning of the fabless foundry model. It was
Mm-hmm.
highly successful. Essentially, TSMC took care of the capital costs. It does not own any intellectual property of the
Right.
design that is being made.
Mm-hmm.
But over time, it got better and better in the fabrication side. And in fact, there's a lot more value addition now, which happens in the manufacturing side also. Earlier, a
Mm.
lot of the profit margin was captured by the design companies only. But
Right.
because technology has become complex, there are leakage effects at 3
Mm.
nanometers, 4 nanometers. So the way you construct the chip itself, the transistor itself has become very complex. And
Mm-hmm.
over time, there is value addition which is required in the fabrication and semiconductor manufacturing equipment also. A lot of heavy research goes there. So this is how it happened in the semiconductor industry. So if we
Mm-hmm.
think of the quantum industry. Similarly, quantum capital cost. Say you have a generation one quantum computers now, and
Mm-hmm.
if we are expecting to make millions and billions of them over time, and
Mm-hmm.
every generation will have improvements require heavy capital cost investment. If that is
Mm-hmm.
the setup, then it will likely follow the same trajectory as well.
Right, right. That's interesting. I think with quantum, given that globally we're still looking for use cases and applications. So we don't know, we know in theory what quantum can be useful for, but then we don't yet know how exactly to make it useful. There have been some breakthroughs recently over just this past week that that have has made some progress, but we still don't know. So if we will need it at that scale is still a doubt. And also I want to ask, do you think is there any point in history where a government could have intervened and made a decision on keeping the supply chain concentrated instead of this unbundling? I ask in the sense in because quantum is considered highly strategic at the moment. I wonder if a government can, if there is some point where governments can come and say that we want to keep all of the supply chain domestic.
It That
Hmm.
possibility exists, but it
Hmm.
is very likely to fail, because
Hmm.
in at least I can say from the semiconductor industry, when semiconductors began, I mean the
Hmm.
ICs started being made mass produced in the 50s and 60s. There were not many ICs, just like
Mm,
we are talking about quantum today. And there were many
mm,
governments which said, we will, why should this be done in a private place? We will do
mm,
it locally.
mhm,
USSR tried it, China tried it, India tried
mhm,
it. There were many such attempts, and they even began quite well. So China
mhm,
produced its first IC before Taiwan did. So
mhm,
they
mhm,
did get started earlier. But again, Rock's law
mm,
came to hit, right? So how
mhm,
can governments justify?
Right.
reinvesting capital
Mm-hmm.
cost every 4 years.
Mm-hmm.
And initially, the demand will also not be from millions of consumers, right? In the
Mm-hmm.
50s, 60s, how many electronics components were using ICs? So
Mm-hmm.
it becomes challenging for governments to take these projects up. So they did try.
Okay.
Everyone
Yeah.
realized that it is a strategic tech for since the 40s, 50s, 60s, that we
Mm-hmm.
have to do something on electronics. And then when once
Mm-hmm.
ICs were invented in the 50s, this is one really cool thing. We need to
Mm-hmm.
prevent our adversaries from getting it. But
Mm-hmm.
it is
Mm-hmm.
very difficult to control knowledge flows. And
Yeah.
eventually, the countries which succeeded were
Mm-hmm.
the ones which had a dynamic ecosystem, very high R&D, very high
Mm-hmm.
private sector collaboration. So governments did put in money. All governments have
Mm-hmm.
put in money in semiconductors. There has been industrial policy even in the US
Mm-hmm.
in the semiconductor industry, but a lot of it was not happening in Washington, D.C., but it was happening
Mm-hmm.
in the Silicon Valley, which is
Right.
far away from government. So yeah, we
Mm-hmm.
can expect governments to have that view, but
Mm-hmm.
we can clearly see it's not the government
No.
companies which are doing great stuff in quantum also, right? A
Mm-hmm.
lot of the
Mm-hmm.
work is happening outside the government.
Private.
Government has
Yeah.
an enabling role, financing role,
Mm-hmm.
but it is not a core R&D role, which was the case with semiconductors
Mm-hmm.
long ago. So I think it's much difficult to replicate or control
Mm-hmm.
even if you call it strategic, it is difficult to do that because it's not happening within the government, like say
Right.
space
Mm-hmm.
in the 50s or nuclear technology in the 50s. They were
Mm-hmm.
largely government run government projects. But even
Mm-hmm.
even space today has fundamentally changed, and you're seeing
Yeah, it's
private space
privatized.
players
Mm-hmm.
doing the cutting edge things, reusable rockets and things like that, not
Mm-hmm.
government firms.
Makes sense. Okay, if we move on to global choke points in the supply chain, now in quantum, everybody's favorite example is dilution refrigerators, which are maybe there are three, four companies in the world that have established markets, and of these, there is one player from Finland that is dominating. So this is a serious supply chain choke point for anybody that's working on qubits that require cryogenic cooling, so mainly semiconductor qubits and superconducting qubits. And I think a parallel to this is ASML in the semiconductor industry. So could you tell us a little bit about what contributed to ASML becoming such a monopoly and how it is a geopolitical lever today?
Right. So again, go back to Rock's law, right? Why does
Mm-hmm.
Rock's law exist? Because to make transistors smaller and
Mm-hmm.
smaller is a you're really hitting the limits of physics, right? You're
Mm-hmm.
now you will have the transistor channel will be a few atoms apart, and if you want to go to that level of precision, you need to
Mm-hmm.
design machines which can carve out such fine features which are a few atoms apart and reliably, right?
Mm-hmm.
You'll have billions of transistors in per millimeter square, and you need to
Mm-hmm.
be able to design the features of this with
Mm-hmm.
very high precision. And to do that, you require newer and newer kinds of technologies to be able to carve out such special features, right? And that's why
Mm-hmm.
you have something called lithography, and there are various techniques of lithography. So deep
Mm-hmm.
ultraviolet lithography, each of these
Yeah.
represent one particular wavelength, and the
Mm-hmm.
wavelength determines the smallest feature size that you can draw, right? So
Mm-hmm.
the extreme ultraviolet lithography is
Mm-hmm.
one thing which ASML has a monopoly
Mm-hmm.
over, and that's the one which is able to have wavelengths of 13.5 nanometers, and with that you are able to carve out very fine features which are used in
Mm-hmm.
2 nanometers and 3 nanometer chips, which we call it.
Right.
So now, to make this happen, that kind of wavelength doesn't exist naturally. So you needed to have, plasma, and it's a very funky tech, the most complex
Mm-hmm.
machine humans have built, right? Every
Mm-hmm.
single EUV machine takes two airplanes to transport. It costs
Mm-hmm. Mm-hmm.
$400 million for one machine, right? And you can
Wow.
make a just around 10, 15
Mm-hmm.
or a few every year, right? Or 10 to 100. It's
Mm-hmm.
just a small range of machines. So that's the kind of complexity we are talking about. So
Mm-hmm.
are the dilution refrigerators this complex is first the question to ask,
Mm-hmm.
right?
Mm-hmm.
And and how did ASML
Mm-hmm.
reach where it is? So again, it was a very tough journey, right? There were many other competitors.
Mm-hmm.
But ASML also required huge capital reinvestment here, and it was on many occasions it was like this EUV especially was seen as
Mm-hmm.
something which will never succeed.
Mm-hmm.
It went on for too long. But it made some strategic acquisitions in 2001. It acquired a company called Silicon Valley Group, SVG. And after
Mm-hmm.
that, to maintain high levels of R&D reinvestment,
Mm-hmm.
it was backed by its customers, right? So TSMC,
Mm-hmm.
Samsung, Intel, they bought
Mm-hmm.
equity in ASML and kept it afloat. So you
Mm-hmm.
do need that kind of confidence by customers willing to, and these are private players, right? So in fact,
Mm-hmm.
Intel, Samsung, Taiwan, none of them are in Netherlands, but they
Wow.
ended up
Mm-hmm.
supporting a company which was in Netherlands, which was at
Mm-hmm.
the forefront of this. And also we have to remember, it's not as if ASML itself is Atmanirbhar or self-sufficient. It
Mm-hmm.
depends on many things from
Mm-hmm.
Taiwan. The chips which are used to make the machine
Mm-hmm.
EUV machines will come from Taiwan. The mirrors which are used to protect the light which is
Mm-hmm.
generated to carve out these
Mm-hmm.
once they are emitted from the plasma. That is also coming from Germany, Carl Zeiss.
Mm-hmm.
And so there
Mm-hmm.
are, they'll have a huge list of their own suppliers which are not within Netherlands. So
Yeah.
that's how
Mm-hmm.
it became what it became over time. And it's also EU. It has monopoly only in EUV, not in
Mm-hmm.
DUV. So today, if you have to
Mm-hmm.
make a 28 nanometer chip, it's not that ASML has a
Mm-hmm.
monopoly. There are other players
Mm-hmm.
also in it, but at the most cutting edge, it does
They,
have a monopoly. So that's
I
how I
see.
would put it.
Okay, okay. And now that, okay, if it, since it has monopoly in the cutting edge, um, how does the geopolitics then translate? That I've read a lot about the conversations between US pressuring the Netherlands not to export to China, and there's been a lot of activity there. But could you walk us through maybe a bit of what happens when a monopoly like this exists?
Yeah. So this is really the uh, high end of. um, uh, okay, let me rephrase it. So the way it operates is because these machines are very easily tractable. There are only a few which
Mm-hmm.
are made every year. You
Mm-hmm.
can put controls on them, right?
Mm-hmm.
Unlike say chips, which you
Mm-hmm.
can smuggle easily. It can. So this is one domain where first detection is very easy. Second,
Mm-hmm.
the acquired knowledge required to
Mm-hmm.
duplicate something like this is very high, right? Like we
Mm-hmm.
discussed, ASML itself had 20 years of research on this. So if I stop it from going to you, it's not very easy that you will be able to develop it, even if you have a lot of money. Right? So
Mm-hmm.
that's why it operates as a powerful geopolitical leverage point. Unlike,
Mm-hmm.
let's say, if I stop some minerals from going to you. Over time, you will figure out
Mm-hmm.
alternative substitutes easily. We have had many such because the
Right.
acquired capability for you to make a mineral which I have won't be that high. You will
Mm-hmm.
learn it. But for a machine like ASML, with the patents that they have, with the collaborative research that has happened over 20, 25 years, it is very difficult to displace it and learn it quickly. So that's why it is
Right.
the most powerful geopolitical leverage in the semiconductor supply chain. Now,
Mm-hmm.
when US-China relations started worsening, and
Mm-hmm.
one of the tools that the US used, amongst many other restrictions, was to
Mm-hmm.
tell ASML to stop supplying EUV machines to China. ASML
Mm-hmm.
still supplies DUV machines. ASML still
Mm-hmm.
has one of its biggest offices in China, but it doesn't supply the most cutting edge machines, which are used
Right.
in advanced chips and the AI training chips, GPUs, right? So
Mm-hmm.
that's where it is. But again, you can see this is not a full ban. There is still
Mm-hmm.
DUV machines of ASML are going to China. There are ASML still operates. So it's
Mm-hmm.
we have to be careful about putting these kind of wholesale bans, because they don't they are never completely watertight as we would want
Right.
them
Right.
to be.
Right.
In fact,
Mm-hmm.
so the Netherlands
Mm-hmm.
became a player in this domain only because of ASML, right? Otherwise, no
Right.
one would have cared for Netherlands as a player
Mm-hmm.
in this segment. But because it has ASML, it does have some cards to play. It has some
Mm-hmm.
leverage. But you should also remember that ASML itself as a company relies on, it has to make profits. It has to
Right. It's
survive.
mm-hmm.
So
Mm-hmm.
if its main if China is its main customer base, and you
Mm-hmm.
say you can't supply to it, it does affect their bottom line, their margins. So in fact,
Mm-hmm.
the companies try to push their governments that, allow us to do some things, allow
Mm-hmm.
us to supply some things. Like Nvidia has been asking the
Mm-hmm.
US to allow them to sell chips to China. So these
Mm-hmm.
kinds of tensions always happen between governments and their companies, and you're seeing that play out. Right now,
Mm-hmm.
ASML is okay because there's a huge demand. There are
Mm-hmm.
fabs being built across the world, but
Mm-hmm.
this industry is prone to lots of cyclical movements. So there will be
Mm-hmm.
some overcapacity, like in matured nodes, it is quite likely. Then once there is overcapacity, firms will not buy as many chip and as many machines.
Mm-hmm.
Then that's when it will really be the test case. So right now we are
Right.
on the high, so it is fine, but there will be a trough as well, and that's when the
Right.
challenge will hit.
Okay, that's very interesting. And this is from the perspective of ASML, but I assume it also applies to companies like TSMC, which produces majority of the most advanced chips in the world today. Um, and I want to ask you, there are different countries are trying to reduce their dependence on Taiwan. Is that a fair assessment?
Yeah.
Um, right. And
So
so how is this? Is this working? Will it work out? How does this work?
right. So
Mm-hmm.
Taiwan again. So
Mm-hmm.
Taiwan's expertise is slightly different. That it's not one
Mm-hmm.
machine.
Mm-hmm.
Taiwan's TSMC's expertise is really in the recipe to make the chips, right?
Mm-hmm.
Because there are thousands of processes, thousands of machines. Remember,
Mm-hmm.
they don't own any intellectual property
No.
on
Right.
the design, right? So
Right.
they
Mm-hmm.
by contracting, they would have signed a contract with Nvidia that they will not be using the GPU design blueprint
Mm-hmm.
for their purposes, right? So they don't own
Mm-hmm.
any of that IP. But
Mm-hmm.
what's their specialty, right? Their
Mm-hmm.
specialty finally is you need to be able to use machines like ASML, use many
Mm-hmm.
other steppers and huge complex architecture, create those
Mm-hmm.
clean rooms so that
Mm-hmm.
you have highly pure operating environments. All that you need to
Mm-hmm.
be able to do and to get the chips which will eventually work. Even a slight
Mm-hmm.
amount of mistake in the process, some impurities will
Mm-hmm.
destroy the chip. So we test this by calling the yield of the chips, right? So yield
Mm-hmm.
should be high. You
Mm-hmm.
can actually make the most advanced chips with DUV machines also. You don't need EUV.
Okay.
You can
Okay.
make with DUV, but their yields will be very low. The reliability
Mm-hmm.
will be low. Some chips might work, some chips might not work. Some chips might work
Mm-hmm.
today, they might not work after 2, 3 years. So you
Mm-hmm.
need to have high reliability, right? And
Mm-hmm.
that's a process innovation. So that's what TSMC has developed over 30, 40 years. They have got really good at bringing all these ingredients together. So think of it as a chef, right?
Mm-hmm.
TSMC is a chef which knows how what to get from ASML, how much of salt to put, how much of some other
Mm-hmm.
ingredient to put, and create this recipe. So
Mm-hmm.
a lot of the TSMC's expertise lies in getting this process right.
Mm-hmm.
And it's a knowledge based innovation. So a
Mm-hmm.
lot of countries now are trying that, but the dependence on TSMC is really something which is risky, because China
Mm-hmm.
Taiwan relations
Yeah.
are worsening,
Yeah.
and if China were to have do a blockade of Taiwan or
Mm-hmm.
invade Taiwan, it would affect other countries significantly. There are
Mm-hmm.
estimates that it will lead to a significant GDP contraction in the world, and there are
Mm-hmm.
major impacts, and every supply chain will be affected.
Mm-hmm.
So
Mm-hmm.
from that perspective, since 2020, there has been an attempt to get
Mm-hmm.
TSMC itself to start shop in other places. So build
Right.
some
Okay.
redundancy. So TSMC has built up things in Arizona, which is a 5
Mm-hmm.
nanometer plant. TSMC Japan is already operating again a 5
Mm-hmm.
nanometer plant. But again, from a Taiwanese perspective, they wouldn't want to let go of the most advanced
No,
capabilities, because
absolutely.
otherwise the world wouldn't care for Taiwan, right?
Mm-hmm.
In the sense
Mm-hmm.
that that's their leverage. So they call it
Mm-hmm.
the silicon shield, and they are
Mm-hmm.
willing to let go of 5 nanometer capabilities to select countries, but not so for
Mm-hmm.
3 nanometers, 2 nanometers, which they are working on. So
Mm-hmm.
now, if tomorrow China were to invade Taiwan,
Mm-hmm.
what would happen, right? My
Mm-hmm.
guess would be there would be some plan to evacuate some of the top
Mm-hmm.
Taiwanese talent in
Mm-hmm.
other TSMC locations, because, as I
Mm-hmm.
said, a lot of it is knowledge expertise,
Right.
which
Indeed.
will have. But still, to put together that entire complex machinery and that
Mm-hmm.
recipe will take time in any other place. So
Indeed.
if
Mm-hmm.
it's still a 1, 2, 3 year hit. We'll not
Mm-hmm.
have the most advanced chips. We will have them, but they'll be at such low yields that their costs will
Mm-hmm.
significantly increase, and the numbers of GPUs that you want will be significantly lower than what we are able to do.
Okay. So what you're saying, the reason Taiwan has been able to succeed, or TSMC in particular, is because they've got the process right. They're able to scale these most advanced chips. I want to ask about India, and you've written extensively about the history of semiconductors in India, and there are several mechanisms that contribute to the industry being bolstered or failing in the country. But I want to look at it from the lens of what lesson it has, because we're now trying to build indigenous quantum hardware capability. So, can you tell us a little bit about what lessons, when India is trying to enter a critical technology supply chain that already has stronger ecosystems elsewhere in China, in the US, in the EU? What lessons can we learn from what we've seen in semiconductors before?
Yeah, so the first thing is none of this should happen within the government. That is, to
Okay.
me,
Mm-hmm.
very clear. That's what happened in semiconductors. We began with
Mm-hmm.
BEL and SCL. Both were trying
Mm-hmm.
to manufacture semiconductors, but then Rock's law hit them hard. And after that, the government said, how can I this give money to two government firms? From a government perspective, it is waste of
Mm-hmm.
money. But competition is good if the source of money is not the same
Mm-hmm.
entity. So in that sense, government then said told BEL that you only do integration, don't make ICs, and SCL was the only firm which was meant to do chip fabrication.
Mm-hmm.
And eventually it fell far behind, right? Because it was just one player. We were also operating in a closed environment. SCL required machinery to be imported. That took a lot of time. It didn't have enough money to do that because there were foreign exchange related restrictions, so it couldn't do that. And finally, it was never aiming to compete with the TSMCs,
No.
etc. Their
Mm-hmm.
aim was, okay, we are a government-run firm. We will supply the demands of the government, which would be,
Mm-hmm.
say, defense or some space related, which will be a small demand. You don't need a volume manufacturing for it. You can
Mm-hmm.
just do that with an SCL kind of facility. So their vision was never global. Their vision was
Yeah.
never to be the world's best. And that's what happens with government-run companies. So
Mm-hmm.
you first thing you need to do is any of these we need it to happen in private sector firms which are trying to aim to become the best in the world. Just
Mm-hmm.
like in IT services, even though we don't do
Mm-hmm.
any R&D significantly there, but we do a lot
Mm-hmm.
of process innovation
Mm-hmm.
there. And because they are competing with the world, there's no
Mm-hmm.
protectionism. They have survived. We export more software services than Saudi Arabia does oil, right? So in that
Mm-hmm.
sense, all that has happened because of no protectionism. So we don't need
Okay.
protectionism. It's if the capital costs are high, we would require an enabling business environment.
Mm-hmm.
We would require companies to be probably some amount of initial capital funding upfront
Mm-hmm.
capital support might also be required. So maybe the
Mm-hmm.
government deciding setting up a few challenges, like you require quantum computers of XYZ qubits
Mm-hmm.
for a specific purpose, and then that challenge can be thrown open to multiple players. You can fund some part of it. Those kinds of things are okay as a financing mechanism,
Mm-hmm.
but not as
Mm-hmm.
a production mechanism. Government shouldn't produce these things, and we need to keep ourselves integrated with the global supply chain. We should
Mm-hmm.
understand that we will not be able to do this alone, and I think that the government gets it. That's why
Mm-hmm.
IBM, etc., there are global players which are also doing quantum related work within India, right? So that's a
Mm-hmm.
good step. And yeah, we should not think of it as an isolated thing we'll do. What we would want to do is look at what are some core capabilities we require for defense space
Mm-hmm.
related things that we will
Mm-hmm.
have to build ourselves.
Mm-hmm.
The other thing, other than that, you would want to look at is where is our comparative advantage in this supply chain, right? As this
Mm-hmm.
supply chain becomes more and more complex, there will be
Mm-hmm.
certain segments in which we'll have the right enabling conditions, the talent, the
Mm-hmm.
VC ecosystem. We will have the enabling environment in terms of whether you are able to set up those kind of companies or not, whether do you have the materials or not. So once those comparative advantages are appearing, we need to double down on the segments where we have the
Mm-hmm.
advantage, right? So I don't know, maybe cryogenic electronics design, maybe
Mm-hmm.
calibration software. There might be
Mm-hmm.
certain qubit control algorithms where India might have an edge. So once you occupy certain spaces in the supply chain and you're really good at it, then it becomes difficult for other countries to deny other things to you because you are
Mm-hmm.
really dominant in one supply chain. That's how we have to think of it. We can't build everything on it on our own, because there will be anything. If anything we've come to know over the last 3 4 years is no country is fully self-sufficient. There is always a choke point somewhere or the
Mm-hmm.
other, because you will be dependent on some one material, one gas which is coming from
Mm-hmm.
some other country.
Okay. Is there any way this deviates? You've written about this extensively for semiconductors, where it's not ideal to be entirely self-sufficient, which is what you're saying. But do you think the logic deviates in the case of quantum in any sense? For instance, I think the biggest fear and the biggest threat, which with the papers that have been released just last week from Google and Oratomic, which is another startup from Caltech, that quantum computers can break current encryption schemes, right? That is the biggest fear right now. Um, and and I assume, I don't know, in the history of semiconductors, there were probably such threats back then when you look at it and you say that, so this was probably also the thinking back then. But does this logic deviate in any sense then, or is it the same with quantum technology as well, with this argument of self-sufficiency that you have?
Yeah, no, see,
Mm-hmm.
even back then, most of the chips which were being made were for the defense segment only. So, for
Mm-hmm.
example, missiles, to make missiles better, you needed
Mm-hmm.
electronics control units, electronic
Mm-hmm.
control units, right? So how will you make that without an IC? So a
Mm-hmm.
lot of the initial development of chips happened because of government demand. So, for
Mm-hmm.
example, Texas Instruments, which was one of the leading companies in the initial time, IC was
Mm-hmm.
uh, developed by an engineer there, Jack Kilby. And a
Mm-hmm.
lot of their initial demand was for either the NASA space program or the Department of Defense or Department of War now, so
Mm-hmm.
Pentagon. So those were the big sources of demand for them as well. So it was
Mm-hmm.
dual use exactly as quantum is today
Mm-hmm.
being considered today. But the key thing is, just like quantum today is being built by private players, there are
Mm-hmm.
all these capabilities are not within governments. They are within universities, within companies, and
Indeed.
with people who are talking across borders. The papers
Mm-hmm.
that are being written are papers across borders. It will be very difficult to sort of put barriers
Mm-hmm.
on them. We will finally have multiple options, multiple things people are doing. Some will get really good in one supply chain segment, and then they
Mm-hmm.
might use that as leverage, right? So idea is, can we build some base capability across the supply chain? We can think
Mm-hmm.
of that now. Maybe that we couldn't do in semiconductors that time because we took a wrong approach in terms of setting things up within the
Mm-hmm.
government ecosystem. But today we can do that in quantum, is think of having at least some base level capabilities across the supply chain. Just like now we are thinking of building a fab, which is 28
Mm-hmm.
nanometer and some assembly unit, which is really starting at the lowest end. And we
Mm-hmm.
are trying to build some base capabilities such that we have the talent ecosystem. People know how to do fabrication, and
Mm-hmm.
we are doing that quite late. We don't need to do that
Mm-hmm.
late for quantum. So we start
Mm-hmm.
with some base capabilities, but we focus on identifying and developing our comparative advantage, which I suppose should be in the design, software, firmware
Mm-hmm.
levels, where we'll be quickly be able to be at least one of the top four or five players.
Makes sense. Makes sense. And speaking about the governance of supply chains, if we talk about bubbles of trust, which you've written about, and these governance tools like the partnerships, like the Quad partnership, the ISET framework, um, even in the context of quantum technologies, there is some work and there are such bubbles that are starting to form. For instance, the Quad. But given the current geopolitical trends, what is the future in the semiconductor context of these bubbles of trust, and where does India stand within them?
Yeah, so this bubbles of trust is a phrase which Nitin, my colleague, had
Mm-hmm.
developed to think of one. If we know, for example, that no country can be self-sufficient, you will
Mm-hmm.
need some collaboration across countries. And
Mm-hmm.
once, if you're skeptical of collaborating with everyone in the world, then you need,
Mm-hmm.
because there are your adversaries also
Mm-hmm.
in this group, you want to be able to think of which is the minimum viable group of partners you can start off with. And that's
Mm-hmm.
where the bubble of trust argument begins, that you start with a small group of countries who don't need to be convinced about the
Mm-hmm.
importance of a technology and the politics of getting together and doing things. And then you expand the bubble as you
Mm-hmm.
get more confidence and you develop more things. So it is start
Mm-hmm.
small, do something useful, then grow the bubble.
Mm-hmm.
That's the idea. And you're seeing a lot of bubbles of trust forming around a bunch of technologies, right? Like there are,
Mm-hmm.
in fact, there is a Chip 4 alliance. There is, yeah, trust framework now between India, US.
Mm-hmm.
There's the India EU Trade and Technology Council. There's a US EU
Mm-hmm.
Trade and Technology Council. US has signed a number of MOUs on critical minerals with a number of
Mm-hmm.
players in Southeast Asia. So, uh, technology cooperation through these kinds of arrangements,
Mm-hmm.
these are bilateral or multilateral arrangements, has really shot up. right? Because
Mm-hmm.
countries realize that you can't do this on your own and you need some partners in
Mm-hmm.
it. And it will only increase. It's
Mm-hmm.
unlikely to decrease. It's just about identifying which kind of blocks work for you. So you didn't need these blocks when the entire ecosystem was largely free flowing, right? So you had
Mm-hmm.
no controls. So countries didn't need to think of, why should I worry about the rare earths coming from China
Mm-hmm.
or the some specialized magnet coming from Japan. I can
Mm-hmm.
just the companies can buy it. The governments have no role to play. But now
Mm-hmm.
because if all these supply chains have become weaponized, there is a
Mm-hmm.
role for governments to ensure that some redundancy is developed. And that's
Mm-hmm.
where governments are trying to make it easier for companies to form this. Ultimately, it will still be have to be done by companies only.
Mm-hmm.
Governments can do things like stockpiling
Mm-hmm.
for certain materials, certain machines for short-term shocks, right? And they can
Mm-hmm.
probably encourage some joint research across countries, companies in different countries. They can enable easier movement of talent in the selected bubble of trust countries. But
Mm-hmm.
eventually, it's the biggest thing is companies are now realizing on their own that
Mm-hmm.
you need to be able to develop redundancies. You can't have just one supplier in China
Mm-hmm.
as your source. You need to have multiple suppliers for your own interest, not because the
Mm-hmm.
government is saying so. And that is what is the major thing we have to track.
Mm, okay. Okay. You've mentioned rare earths. And speaking of rare earths, in the past 3 years itself, there have been several waves of export restrictions from China on critical raw materials like gallium and germanium, and also antimony, bismuth, tellurium, molybdenum. All of these raw materials that are essential for semiconductors, but also super essential for quantum hardware to build different kinds of quantum hardware. So, what is the impact of such restrictions? And then I also want to follow up with where does India stand? We do have some capability in some of these minerals, but then what would it take for us to really start to supply high quality, high grade minerals?
Yeah, so gallium and germanium, as they are not rare earths, but they are like
Mm-hmm.
critical minerals. We use them
Mm-hmm.
for specific chips,
Mm-hmm.
especially high band gap semiconductors
Mm-hmm.
and high power requirements. So that's where they are used. China did put restrictions on gallium germanium since
Mm-hmm.
2023. It has also put rare earth controls
Mm-hmm.
since in 2025, and it increased around 11 rare earths are now
Yeah.
controlled. So uh, my assessment is in this is uh, it is a losing battle.
Mm-hmm.
The other countries will find develop alternatives and substitutes. It
Mm-hmm.
is like a card whose value extinguishes the moment you play it. So
Mm-hmm.
they have played this card, and others have are very clear. It is very clear for other companies and countries that you have to find your own alternative, right? And it is
Mm-hmm.
not, I mean, extracting gallium, etc., is not like making an ASML machine. It's
Mm-hmm.
gallium, it's an byproduct of alumina
Mm-hmm.
extraction. It's just that no one wanted to extract it because the extraction takes time. It's also not a it is a slightly complex process. It is a polluting process, and it
Mm-hmm.
requires cost, right? And right
Mm-hmm.
now, if you were just buying it from cheaply from suppliers in China, you didn't want to get into the hassle of it. But because
Mm-hmm.
China has made it clear that these things are going to happen, others are finding alternatives. And the key thing is costs of these materials were too low. And that was the
Mm-hmm.
problem. Because the only players who could supply were Chinese players who were
Mm-hmm.
supplying it at very low rates because of their overcapacity, their subsidies, exchange rate manipulations, etc. Right? So now, because costs are rising, other companies in other countries are finding this more lucrative, and you are seeing things happening. So gallium and germanium, we've just recently done a paper and in which we
Mm-hmm.
find that after restrictions, since it's been
Mm-hmm.
around 2.5 years, what has happened to
Mm-hmm.
the US consumption? Because US
Mm-hmm.
is either sanctions were on supply to US, and we find that the consumption of US hasn't dropped significantly for gallium or germanium, which
No.
means they have
Okay.
found from other places,
Right.
or they have used their reserves, or
Mm-hmm.
companies have built their own reserves anticipating this, because you don't require a lot of it, right? The entire
No.
uh, yearly demand of gallium for US can be fitted in 2 truckloads, right? So it's like,
Mm-hmm.
if you have alternatives, you can stockpile, you can do a bunch of
Mm-hmm.
things. So that is the kind of thing which is being done, and we've had such restrictions from a long time ago. In 1930s, rubber was important. 1950s, mercury was important. 1980s, cobalt was important because it was used for
Mm-hmm.
jet engine alloys. But then people found out carbon fibers, molybdenum, etc. So a lot of these things people find alternatives. So here in rare
Mm-hmm.
earths, probably we'll find a bunch of companies and electric motors which will be either induction motors or motors which
Mm-hmm.
will use ferrite core magnets and not
Mm-hmm.
rare earth magnets. It is an innovation game, but I see that some alternatives of that nature will come up in the next 4 5 years. Now,
Okay.
where
Mm-hmm.
is India in all this, right? So
Right.
India, for example, I mean, the critical minerals list is a long one.
Mm-hmm.
India has identified around 47 critical minerals,
Mm-hmm.
including the 17 rare earths. It's a long list, and there's a national critical mineral mission too now, which is trying,
Mm-hmm.
just like with quantum, there's a national quantum mission there. There's a national critical mineral mission which is trying to enable a lot of the extraction, the
Mm-hmm.
refining, and recycling. These are the three
Mm-hmm.
stages. The challenges are quite similar as in other domains. Extraction is
Mm-hmm.
mining, it is environmentally polluting, it takes a lot of time, it requires a lot of permission. So it is very difficult to do in India. And even though we do have monazite sands which have
Mm-hmm.
large reserves of rare earth, but we had other challenges because those monazite sands also have thorium. Thorium is important for India's
Yeah.
nuclear 3 stage nuclear
Mm-hmm.
cycle. So thorium extraction is tightly controlled. It is only with
Mm-hmm.
one government company. So we've been making a point that it should be thrown
Mm-hmm.
open to private players with some strict controls on giving the thorium back, stockpiling the thorium, but using the other ores which have
Mm-hmm.
rare earths to be
Right.
processed by the private companies. So that
Mm-hmm.
is one challenge in the extraction stage. And refining, now the government is giving upfront capital investment for
Mm-hmm.
players to do that. And we are also trying to build a rare earth magnet plant in
Mm-hmm.
Vishakhapatnam. The IREL
Mm-hmm.
is trying to build. So these are things which are happening. Ideally, we
Mm-hmm.
would want to, again, because the costs are increasing, it is actually lucrative for private players to get into the game. In refining, urban mining is a very good segment, for example, because we'll have huge amounts of lithium vehicles. Lithium can be
Mm-hmm.
reused, right?
Mm-hmm.
From batteries, the rare earths, each of our machines, each of our phones, each of our cars will have huge amounts of rare earths. And these
Mm-hmm.
don't get extinguished like oil,
No.
right? So you can
Mm-hmm.
recover a lot of this. So
Mm-hmm.
in fact, recycling might be one comparative advantage segment for India. So we
Mm-hmm.
would want a
Mm-hmm.
lot more investment focus on that.
Mm-hmm.
And other segments, you just need to enable things. So that's how I would think of it.
Okay. Okay. So I just want to ask now, because we're short on time, but as a sort of summary, um, if since in the context of quantum, this is a new critical technology and its supply chain is just starting to form, specializations have not been concentrated yet, and all of the big powers are still figuring out which architecture, which hardware architecture is the best and what applications it will be used for. Um, India, we have limited capital, and at the moment we have limited hardware capability, but we have a lot of talent, we have some raw material and component assets, and we have certain strategic partnerships. So, based on everything that you've learned from studying semiconductors and being part of the industry, and now studying policy for it, the history, the failures, the choke points, the successes, everything. What do you think India should do? Or what's the single biggest thing India can do? And what's the single biggest thing India should not do?
Yeah, so the way I would think of it is actually many of the solutions lie outside the scope of quantum itself. So what you
Mm-hmm.
would say is if there is talent, most of that talent will go to the US or some other country, right? Because
Mm-hmm.
why? Because most of their customers will be there, most of the VC ecosystem will be there. So
Mm-hmm.
that's a natural tendency for firms to relocate there. So now
Mm-hmm.
what we would want to do is we want to make redomiciling of technology firms easy so that people
Mm-hmm.
sitting there want to come back to India probably or to
Mm-hmm.
file patents in India. Or you
Mm-hmm.
would want them to, we should allow VC funding to come easily, right? There are a lot
Mm-hmm.
of restrictions where VC funds in India cannot take money out of India.
Right.
So they don't even come to India in the first place. They'll sit
Indeed.
in Singapore
Mm-hmm.
and do
Mm-hmm.
things that in India, right? So these kinds of restrictions are what bottleneck us in the deep tech
Mm-hmm.
space. I mean,
Mm-hmm.
from a government perspective. Otherwise, there are lots of other things you can say. Yeah, education also needs to improve. All those are points, but things that governments can immediately do is make these restrictions go away. Easy
Mm-hmm.
to raise money, easy for money to flow across the across borders, easy for VC funds to move money. Once
Mm-hmm.
that happens, you will see a lot more money coming because finally the amount of capital that will be required in this is not something governments can give or any government
No.
can give. They can
Mm-hmm.
just start, they can play a role of a catalyst, they can do some initial research, one prototype.
Mm-hmm.
But if you want this to be a mass technology and really new applications to come up from it, it will have to be done in the private sector and by
Mm-hmm.
companies, which means we need to think of how can we enable many companies in this segment to come up
Mm-hmm.
and what's stopping them from coming. Let's try to start there and remove those barriers
Makes sense.
instead of and then you can for your strategic applications you can always say the for my defense needs or to I
Mm-hmm.
don't know post quantum cryptography or for offensive use of quantum cryptography.
Mm-hmm.
You would want certain applications which governments can fund for government use. That is
Mm-hmm.
fine. There can be challenges for this. There can be money backed. I think the government now largely knows it. We have a national quantum mission. There is the research and development incentive under the ANRF. Then
Mm-hmm.
for defense related applications, we have IDEX. So we are very different from the India that was 20, 30 years ago, right? Where we were
Mm-hmm.
limited in many ways. So
Mm-hmm.
this is a period where the s- the takeoff period for quantum technologies can be much shorter than it was
Mm-hmm.
for some of the other things, given where we are in our developmental journeys. So that's what I
Right.
would say we have to do.
Mm-hmm.
What we shouldn't do is again, think of restricting it way too early. So because
Mm-hmm.
this is dual use, then we'll say, one CSIR lab in India will do it. Those kinds of things we shouldn't be doing.
Mm-hmm.
Other than that, it has to be placed. If there we have to think of two, three uh, levels down. Even for research,
Mm-hmm.
are there
Mm-hmm.
quantum related courses in our
Mm-hmm.
universities? If there
Mm-hmm.
aren't, can we have in fact, for example, there are can we invite foreign universities which are good in this segment to set up
Mm-hmm.
campuses here? We are government has now allowed campus foreign university campuses to open, right?
Mm-hmm.
But so we would want them in cutting edge tech domains. So
Mm-hmm.
those kinds of things will create the a large number of researchers who can work with the principal investigators and then do cool things, right? So all
Mm-hmm.
that requires it's a 15, 20-year journey where we shouldn't think
Indeed.
of one product or one milestone, but build these
Mhm.
capabilities across. Then companies will do their own things.
Makes sense. And I hope with the National Quantum Mission and everything that's going on now, it certainly seems like this is the direction in which things are going. But on that note, thank you so much for your time. And this conversation was extremely insightful. I've learned a lot, and I'm sure our listeners will also have learned a lot. Thank you so, so much.
Thank you, Priya. All the best.
Thank you.